that better? Yeah. We have a state variable Q. We're splitting it up into a mean. We talked about different types of mean. It could be large scales. It could be a spatial mean, a temporal mean, an ensemble mean, and fluctuations, the Reynolds decomposition. We derived an equation for the mean. Looks like this. Unfortunately, what we needed to know, if we wanted to describe the evolution of the mean, was the effects of the fluctuation interactions acting back on the mean. And depending on your context, if you're doing fluid dynamics, solving the Navier-Stokes equations, this might be called a Reynolds stress type term. If you're doing dynamo theory, so you're solving the induction equation, this might be called the mean electromotive force. But it's always the fluctuation going to the mean. I then went on to spend an awful lot of time last lecture thinking about the fluctuation equation and saying that you know, there are two linear bits. This one's formally linear or quasi-linear. It depends on Q bar, but that's okay. It's linear in Q prime. And then there's this horrible nonlinear term, pain in the neck term, which we'd quite like to get rid of. And I talked a little bit about how you might get rid of it. If you get rid of it, you have the quasi-linear approximation. And then what we wanted to do was have a look at how good the quasi-linear approximation was. And we showed that actually you could improve on the quasi-linear approximation in the so-called generalized quasi-linear approximation. Why do we need to know about Q prime? Of course, we really need to know about Q prime to get this term here. But actually, we don't need to know Q prime. All we need to know, so Q prime, remember, is a small scale thing or fast thing. What we really want to know is the effect of Q prime on the large scales. So you want to try and avoid, if you can, solving at the small scales, because you know that's the whole point of doing this. You don't want to solve on a massive range of scales. So what you could try and do is just try and work out equations for this term. And this term is only on the large scales, okay? And that's what we're going to do today. Okay, so what are the options? Well, we could just say, I'm going to call that term that, so I don't want to keep writing this thing out. The Reynolds stress term or whatever you want to call it. I'm just going to call it curly R. Of course, this could be a tensor, it could be a vector, it could be whatever. But this is just a schematic, so I don't have to keep writing it out. So what could I do? Well, I could just postulate. If I only want to solve on the large scales, I could just postulate some kind of functional form for it in terms of what I know, and I know Q bar. So I could just say, R is R of Q bar, and I'm just going to try and work out some sensible functional forms. And remember, okay, this R could be any kind of operator. It could be a vector, differential operator, that kind of thing. But it just depends on Q bar. And this is the kind of thing Baylor was talking about. So you can postulate some dependence if you want to keep something that you think is a good property of your flow. And you might choose a different thing depending on what your mean fields are. So sometimes this is called a grid parameterization, because what we're doing is we're parameterizing the effects of the small scales on the large scales. We're choosing a function to do this. Now, you can critique this approach by saying, well, how am I going to try and pull one of these things out the air? In particular, this thing R may depend on the Q bar sometime in the past, and that's sometimes called memory. So for example, or it may depend on Q bar at some other location in space. So for example, in the UK, we keep a close eye on the weather on the East Coast. So whenever you guys have a storm on the East Coast or a hurricane, we know 3 days later it's going to land on us, right? We're going to get some bad weather. And that's, you know, the weather in the UK being a function of the weather on the East Coast 3 days earlier and however many thousands of miles away. So sometimes this has to be a function of Q bar at previous times as well as the current time. And sometimes it has to be what we call non-local in space. It's a function of Q bar at other positions, right? So these are quite hard to work out. But sometimes just writing this thing down can give you a lot of information. So I'm just going to do an example, which essentially was the workhorse of dynamo theory for about 40 years. So let me write this down. So remember the induction equation. Which looks like this. And I'm going to do exactly what I did before. I'm going to do a Reynolds decomposition. So I'm going to say U is U bar plus U prime, and B is B bar plus B prime. Okay. And traditionally what we do is we set U bar equals 0 just to make the algebra easier. So I'm just going to set that to 0. There's no mean flow, but there is a mean field. I want to describe the evolution of the mean field. And so I write down the equation for the mean magnetic field. So I just take the mean. So I get this is the term we're interested in. And I'm going to call this thing E, which is what I call curly R in the general case. U prime cross V prime bar. Okay, and that's the mean electromotive force. And I could write down an equation. I'm not going to write it down for you. It's in the notes, but I'm not going to write it out for the fluctuations, which I'm not going to write down. There are linear terms, and there's a pain in the neck term. Okay. So at this point, we can say quite a lot. So the equivalent of saying R is R of Q is writing E as some function of B bar. You know, and perhaps it's derivatives or whatever. And the answer is yes, we can. And this is a special case because formally the fluctuating equation, which I'm going to write out, which I'm not going to write out, is linear in B bar. So we can just do this by appealing to linearity. And we write out, it's now a kind of famous ansatz. We write, well, E is a vector, so we simply write a linear Taylor expansion. So we write EI is alpha ij times bj bar plus beta ijk. There's a few technical details, beta ijk dbj dxk, which if you're interested, you can look up in some of the papers I've put on the thing. So we pose a Taylor expansion. You can say an awful lot just from having put this Taylor expansion together. So the idea of doing all of this dates back a long way to Parker in 1955. This is the same Parker that Ellen's been talking about, the guy who essentially did everything in astrophysical fluid dynamics, and to Steenbeck, Krauser, and Radler. They formalized Parker's argument. in 1966. But we can say an awful lot. A couple of things to note. Okay, what do these terms mean physically? Well, you want to just keep in mind that the E appears in a curl. The simplest case for homogeneous isotropic turbulence, which again I agree is not necessarily the case, if we wrote down simple tensors that satisfy the right things, I can write these as alpha, delta, ij, beta, epsilon, ijk. If I did this, what this one would look like is the curl of a curl, which looks like a diffusion operator, as we saw the other day. So this is like a diffusive term. And this term looks like a generating term. Okay. Now, this isn't really telling us very much, because of course we have no idea what alpha ij and beta ijk are. They come from solving the fluctuating equations. Except we can say one thing. These two vectors have different transformations if you go from a left-handed to a right-handed set, because this one has a cross product in and this one doesn't. So if I change from a left-handed to right-handed set, this one changes sign and this one doesn't. So in particular, if I'm in a rotating system, then I'm going to get a different sign for alpha, depending on whether I'm in the northern or southern hemisphere. So this tells me automatically that alpha changes sign at the equator, because it depends on the Coriolis force, or depends on whether, whether you're left-handed or right-handed. And alpha is 0 if you're not rotating. So I haven't done any work, but I've already got two very important results out. So whatever I choose as a plausible candidate for a function for alpha has to change sign at the equator. And if the planet or star is not rotating, alpha is 0, and I just have what's called turbulent diffusion. So this is very interesting, and these kinds of models were solved for an awful lot. What people did was they chose plausible profiles for alpha and for beta based on what they thought was going on, and you could solve just for the large scales. And here's a solution. This is a solution from a so-called mean field model of a butterfly diagram showing the evolution of a large-scale magnetic field that does all sorts of interesting things. We have a dipolar magnetic field here that occasionally dies out in a kind of more the minimum type thing, and then kind of reestablishes itself, perhaps with a different symmetry. These models, they're very ad hoc, but they've enabled us to understand an awful lot about the evolution, say, of the sun's magnetic field. Okay, so that's all I'm going to say for the minute about postulating a form. Just kind of saying, I'm just going to choose R is R of Q bar, or E is some function of B bar in this case. Okay, does anybody have any questions? Yeah. Sorry, can you say that again? You don't. These are in no way predictive models, because what you've done is you've just chosen a functional form for alpha. And so the solution is undoubtedly incorrect, but it does tell you something about the dynamics. If you solve for these things, and then you solve self-consistently for the rest of the large-scale modes, it tells you how a large-scale mode might interact with other large-scale features. I'm not going to get into this, but the reason people did this dates back to 1934, and there's a theorem by Cowling, which says a dynamo can't be generated by anything other than 3D mechanisms. So in 1934, that's it, game over. There's nothing you can do. You're not going to solve 3D problems in 1934. So in order to circumvent this problem, Parker thought, well, what if all the non-axisymmetric bits are on the small scales, and we can just solve for axisymmetric things on the large scales? And that was a breath of fresh air for the theory. And essentially everybody was doing mean field modeling until people could do three-dimensional calculations, which was really only the 2000s properly. Yeah, Nigel. Yes. Yes, that's right. There's an awful lot you can say close to bifurcation points. Actually, for very thin layers, the equations become nearly self-adjoint, and then you can say that you'll get certain mode interactions. So there's a lot you can say just from bifurcation theory. Yeah, exactly. Normal. My PhD was all about normal form behavior for these kind of, yeah, exactly. Wow. Okay. So that's about all I'm going to say for just postulating the form. What we could do, of course, is not just postulate. We could go away and solve it. We could go away and solve for, well, in this case, let's think about it. We could solve for E. Okay, so what would that look like? So the key, let's stick with the dynamo example, is E. If we know E, we know everything. So we'd like an equation for it. So of course, let's just write out the equation for it. So dE by dt is d by dt of u prime cross b prime. Well, okay. So we can all do the product rule. Okay, everybody happy with that? So let me just be clear, this is dt of u prime cross b prime, dt b prime cross u prime. Well, this means we're going to have to go and figure out, have a look at the equation for b prime. And let's just think about this for a minute. What I'm going to do is I'm going to take that equation for here, d by dt of b prime. I'm going to, in this case, cross product, but let's just think of it as multiply through by u prime, and then I'm going to take an average. So I take this equation, I multiply through by u prime, or cross product with u prime, and then take average. Okay? But let's see what that would happen. I'll go back to the q prime case. So imagine what I'm doing now is I'm taking that second equation, I'm multiplying through by q prime and averaging, okay? So I'm not going to go into any details because I will do later on, but let's just see heuristically what's going to happen. I multiply this term by q prime and average. So I'll take the q prime in, and I'm going to get something that looks like dt q prime average, right? So this term is going to look like, okay, maybe I will just sketch. So if I multiply through by q prime and average, so this term is going to look something like dt q prime bar, schematically. I'm going to take this one, and these two are linear. Okay, so I multiply by q prime, it's a linear function, so I'm going to get something that looks like a linear operator a linear operator acting on Q prime bar. Same here, I won't write out this one again. Yeah, so far so good. Then this pain in the neck term, well, I'm just going to get Q prime somehow multiplied schematically by G, Q prime bar. Okay, so I've got, so imagine this is what I'm trying to find. This would be my E or my R, whatever I want to call it. So I've got d by dt of R is a linear operator acting on R plus something that involves 3 Q primes. These are sometimes called triple correlation. And therefore, I'm going to be in trouble, okay? I'm going to be in trouble because I need to know the evolution of essentially Q prime bar. Okay, so I might write out an equation schematically for dt Q prime bar. And I could keep doing that, but at each order, I'd bring in a higher polynomial or whatever, higher order for the Q primes. And this is called, okay, depending on what kind of expansion you're doing, sometimes it's called a moment expansion. This is called it's going to be called a cumulant expansion in a minute. And you can see we have the usual closure problem that at some point we have to close the system. We can't keep going down the system and solving for higher order cumulants. Unless this term's 0. If this term's 0, this term's 0, that's it, we're done, right? So you can see why I spent an awful lot of time trying to get rid of this term and thinking about cases where this is 0, okay? But you don't have to do that. And what I'm going to do is show you a way of getting these equations without going through all this mess, going through some other mess, actually, but still, okay. Okay, so what we're going to try and do is we're going to try and solve the equations essentially for Q bar and for Q prime bar, essentially. And what we're doing is we're solving for the statistics. We're going to be solving for the mean. This one, because we want to be non-local in space, is going to be the 2-point correlation function. This would be the 3-point correlation function. And we're going to try and do that. Okay, at this point, I'm going to go over to the screen. Okay, so why might we want to solve for the statistics? What have I done with my pointer? So, I don't know, this is a nice quote I got from Brad, from Lorenz. He says, more than the theoretical procedure, numerical integration is also subject to the criticism that yields little insight into the problem. The computed numbers are not only processed like data, but they look like data. And the study of those may be no more enlightening than the study of the real meteorological observations. An alternative procedure, which does not suffer this disadvantage, consists of deriving a new system of equations whose unknowns are the statistics themselves. Okay, it's a nice thing to do, and it's not a new idea, of course. And Lorenz really nails it here. This procedure can be very effective for problems where the original equations are linear, or indeed quasi-linear, okay? But in the case of nonlinear equations, the new system will inevitably contain more unknowns than equations and can therefore not be solved unless additional postulates are introduced. So Lorenz says in 2 paragraphs what I've spent 2.5 lectures trying to say. You know, there you go. This brings forward the idea of using your computer power not to solve for the dynamics, but to solve for the statistics. And we call this direct statistical simulation. So why, coming back, why might you want to simulate the statistics? Well, I think I've made the case quite well. You're only solving equations on the large scales, whatever that means. But of course, there's no free lunch. There's a trade-off here. The trade-off is that in this case, we're going to be trading off not solving on the smaller scales to increasing the dimensionality of the problem that we have to solve. So whether that's a winner or a loser, we'll find out a bit later on. The other thing which is very useful is that statistics evolve slowly in time or not at all. I mean, these are the statistics rather than the rapidly varying fields themselves, and hence may be described by a fixed point or at least a slow manifold. So we might have a slowly varying system, in which case we could possibly take massive time steps if you're doing your calculations. And this is a hope, but I think it's probably true, is that statistics are probably less sensitive to changes in the underlying parameters than the detailed dynamics. So probably the mean, if you change some parameters, the mean flows change less quickly than the fluctuating flows. Okay, so there's something to be said here. In geophysics and astrophysics, you have to be a bit careful because the correlations, meaning these R's, if I'm thinking about it in this case, they're usually non-local in time. So they may have this memory effect and possibly in space. And they're also highly anisotropic and inhomogeneous. We talked about these things not being homogeneous isotropic turbulence. So whatever statistical formulation we come up with should respect this. And we'd also quite like them to respect conservation laws. And remember, I told you that if we got rid of this term here, we automatically satisfied conservation laws. And this is not a new idea. So there are any number of people who've looked at this. Okay. So what could you do if you want to simulate the statistics? And I'll come back at the end to a way which kind of mimics the kind of things I've been doing over here. Well, you could try and simulate the PDEs, and I'll show you some examples of that a bit later on. So what you would probably do is derive the Fokker-Planck type equation and then try and solve it. And there you're doing a trade, as I'll show you. When you take your dynamical system, you make it a Fokker-Planck equation, you're increasing the dimension of the thing you're trying to solve, but you're trading a nonlinear low-dimensional problem to a linear high-dimensional problem. And whether that's a good thing to do or a bad thing to do depends on the system, I guess. Okay, I know Freddie talked about large deviation theory. If you want to talk about the rare events, the things that are only going to happen at the tails of your distribution, there's a whole other thing you can do. But what we're interested in is the low order statistics. So we're interested in means, 2-point correlation functions. So these are the things that kind of define the bulk of the distribution, if you like. Okay, so let me just try and fix some ideas before we have a break, bless you. Okay, so what about simulating the PDEs? I think you're probably all happy with this kind of thing. So what you might do is you might start off with some lots of different initial conditions here. At time t is equal to 0, so I can work out a probability, density function or whatever, at x is equal to 0, sorry, at x and time t is equal to 0. Of course, these trajectories will move around in the flow. So if the equation that describes their evolution is dx by dt is v. I've called it v because to be reminiscent of a velocity, but it's any function plus perhaps some stochastic term. Then these things will move around under the flow and jiggle a bit due to the stochastic term. We'll get to an invariant distribution at large time t is equal to large. And I think you all know how to do this. If you do this, you can work out the evolution of the probability of p. So it looks like this Fokker-Planck operator acting on p, and this is the term which you get because of the dynamical system, and this is the term you get because of the stochastic term. Okay, so what have we done? This is probably a horribly nonlinear function, but this equation here is linear in p. However, this, if we're thinking of having a finite dimensional set of equations, is a set of ordinary differential equations, and this is a PDE. So I've turned my ODEs into a PDE. So I've traded nonlinearity for dimension. So let's do an example. So this is an example from from fluid dynamics, the Lorentz equation. So Nigel talks about what happens is you increase the Rayleigh number in convection, you get a bifurcation, and then lots of interesting things happen. And if you do a so-called Galerkin truncation of two-dimensional convection, you derive the famous Lorentz equations. Have you all seen the Lorentz equations before? The prototype for chaos. Okay, I'll show you what they do in a minute. All I want to say is that these are the deterministic terms here, and then we've added the possibility of having noise here. And the question you might ask is, what does the PDF look like? So let's show you. So I've got a lot of initial conditions here. Oops. Okay, and they all shoot off. And then eventually they settle down for certain parameters into this attractor. Have you all seen this attractor before, which looks a bit like a butterfly? Okay, now we're going to zoom in so we can see really what it looks like. So they all lie on an attractor in phase space, which is this kind of winged. So the question then is, can you solve a Fokker-Planck equation to try and get the probability distribution function for the final attractor? So this is something Brad did with a student a while back now. So he solved this equation, and essentially now what he's solving is a three-dimensional partial differential equation. So he's taken three ODEs and turned them into a three-dimensional partial differential equation for different amounts of noise. I'm not going to go into details. So this is the PDF you get from DNS. This is what you get from DNS plus adding a little bit of noise, and the noise actually acts so as to smooth some orbits here. You can see, so you have a hope of getting your Fokker-Planck equation to work well. And of course, if you don't put noise, Nigel's talks a lot about the danger of getting rid of, the highest derivative in a set of equations. We don't want to particularly do that, so it's helpful to add noise. And these are the solutions of the Fokker-Planck equation. So you can see they do pretty well. So that's one way you might want to simulate statistics. However, as you say, we've traded something. We've traded a huge increase in dimensionality for nonlinearity. Okay. Has anybody got any questions about that particular? Because Brad's in the audience, so we can always ask him. Yeah. Sorry, can you say that again?
Sorry. So this equation is the calculus. How do you do things like calculation?
Well, okay. So my feeling is perhaps you can't, unless you say that there are some scales that you haven't resolved, which could be modeled by a stochastic term. So people are always modeling unresolved scales by stochastic terms. Although I think Nigel's going to comment, but I think if the solution is chaotic and there aren't very many unstable periodic orbits lying around, you might be able to get away with just doing it anyway. Sorry, Nigel, did you want to comment on that? Yeah, that's true. Yeah, that's a good question. I guess okay. So what you would really need to know is how is noise amplified, and for that you'd really need to know, how would any numerical errors be amplified, for example. And for that you really need to know the Lyapunov functions of your system. Yeah, your Lyapunov experiments. I haven't. Sorry, Adrian, do you have a question? Oh, because okay, so remember, I'm solving 3 equations here. Here I'm solving a PDE, a 3-dimensional PDE. So I might have to take, in order to resolve the structures, I might have to take, I don't know, 100. How many did you say? 128 modes in each direction. So, yeah. Is it? Yeah. Yeah. Exactly. Keith. Mm. Right. Yeah, that is it. Yeah, possibly. I hadn't thought of it that way, but yeah, that might be a way of thinking about. Yeah. Yeah. Yeah.
So when you get a PDE, it increases the dimensionality.
Yeah.
But when you showed us the whole thing with the ensemble, in the sense that it has a higher dimensionality, is the number of ensemble.
Yeah.
So is the PDE clearly worse? Like if you want to sample the manifold well anyways, is there a wind of like
let's come back. I mean, you know, I've spent 2.5 lectures setting this up. If I was going to say, and it's always worse, you know, you might be a bit disappointed at the end. I mean, you might be a bit disappointed at the end anyway, but yeah. Can we just, yeah, okay. So, okay, so solving for the full PDF is expensive, but in a sense, that's the answer, right? Navier-Stokes equations. Okay, so you have to put it's a PDE, so you have to write things in terms of functional derivatives. But once you've written it down, I mean, you can't solve it, but that is the solution. Okay. But we're not going to do that. What we're going to try and do is say, well, imagine we want to solve for the mean and the correlation functions. So the covariance matrix of X, Y, and Z in this case. Is there a good procedure for doing this? Okay, and I see it's 9:43, which means it's time for a couple of minute break, 3-minute break or so, and then we'll come back and we'll try and see how to do these things and how it links back with this. Okay, see you in 3 minutes.
The noise acts purely as a diffuse term.
Yeah, okay. Because Brad chose noise, which when you put it through the machinery, you know, looks like a straightforward constant times the diffusive term. So it's like white noise, delta correlated. Yeah.
Okay, but you don't put noise. You don't have a PDE. The system does not react. You have a trivial PDF.
If you yeah. No, I mean if you have, okay, the problem is if you do DNS without noise. So this is just DNS without noise. So you get a PDF, but the problem is you get these very sharp features because there's no noise to smooth it out. And so this is, you add a little bit of noise. And so, yeah. Also, I mean, when you're solving this PDE, you really want to have this term here so you can implement boundary conditions and things like that. Yeah.
Also, you get noise, but that's why I was surprised it was
No. Yeah. Could you get spontaneous stochasticity in an ordinary differential equation system? Or, I mean, that might. Sorry?
So,
my student, Dima and Greg, done toy models. I didn't work on code.
Yeah.
So we used part of the RG methods that we had on it. They went to they showed how probability distribution. They could solve it by they could generate it by
Yeah. No, I remember. Yeah. Okay. I'll have a look. Yeah. Thanks.
But this, I mean, this
Yeah. Absolutely. Absolutely.
I'm just thinking that, what you ideally what you'd like to do is some sort of adaptive algorithm where, as you start generating projectiles, the system is then starting to infer what the right noise is.
Yeah.
So what you'd like to have is a sort of
Learning. Absolutely. Yeah.
which you can do. It would be sort of like adaptive incorporating.
Yeah.
Well, I mean, I don't know whether the game is worth to handle, but that way one could do it. I mean, the other thing I was thinking about was there should be, did Brad ever work out like normalization?
I don't know. You'd have to ask him.
I mean, you also say, well, here's a scale, now work out as I change that scale, how do the equations themselves change?
Yeah.
And look at the dynamical system of the flow of the coefficients of the equations as you change those scales, and that's called the beta function.
Right. Okay.
And so, and then you can see, do you float a fixed point, or what the trajectories look like? So you're looking at what is the impact of the effective equation by the system on the scale.
Right.
And so that would be the RG way of thinking about this, rather than saying, because of course before that people did exactly this in mechanics.
Yeah.
Take speed, take some iterations.
Yeah.
Calculate perturbation theory, what energy to do, and then there's your answer. And the whole point about RG was
Get past that.
get past that by doing scale by scale elimination of RG flow. And, that's the next level.
Yeah. Something to think about.
We did talk about it.
Yeah. Yeah. Okay. Probably better get them back in. Okay. We're ready. Come on, guys. Okay. So every morning I give you guys a break, and every morning in the break you deprive me of my tea at my break. So I hope you've left me some tea. Okay, so how are we going to do this Cumulant expansion, or trying to find the low order statistics? So we're going to do it exactly the same way as we did it before. We're going to, what have I done with my stick? If we have in this case, let's say I have my ordinary differential equation system here. So QI, I goes between 1 and 3, it's X, Y, or Z, okay? And I could have some forcing term, I have a linear term, I have a nonlinear quadratic term, and I could have some noise, okay? So what might I do? Similar to before, I'll do some kind of decomposition into a mean and a fluctuation. And I'll define my cumulants as the first cumulant to be the mean of the ith variable, so that we'll have x bar, y bar, and z bar. Cij to be the covariance matrix. Okay, so this could be x prime, y prime bar, could be x prime bar if I is equal to j. We'll define, remember you might need the third cumulant, so I'll define Cijk to be qi prime, qj prime, qk prime bar. I won't go into the fourth cumulant because We're never going to get that far. Okay, and then we write down the equations for the cumulants. And we can do this either by doing the hard work, by just writing down the equations, multiplying through by the relevant thing and averaging. Or there's a way called the hot functional technique, which I've put in the notes that I'm not going to go through today, which is to take essentially moments of the derivatives of the Hopf equation. The Hopf equation is essentially the Fourier transform of the Fokker-Planck equation. I'm not going to go through this today. It's going to be in the notes. So let's imagine we're just a glutton for punishment. We're going to do the hard work. Just keep multiplying through and integrating. And what we can do is we can derive equations for the cumulant. So the first cumulant just looks like this. And so it looks like, okay, so I have the linear term multiplies the first cumulant. And then I get the nonlinear term, and I get, this is a mean-mean interaction, if you want to think of it this way. This, the covariance matrix is representing, you know, the Reynolds stress, the fluctuating, going to the mean. So I need an equation for the second cumulant, and I write it down. I won't go into details. I have a linear term in the second cumulant. I have nonlinear terms involving cumulants I know, but then I have the third cumulant, okay? And this term here, this comes from the noise. I'm not going to get into any detail about that. So really, I need to know what my third cumulant is. So I write down an equation for my third cumulant, and I have a linear term in the third cumulant, some nonlinear terms, and then, of course, I would have a fourth cumulant. And there are various things we can do. We can just give up at that point, or we can perhaps say something about the fourth cumulant in terms of the higher order cumulants. And I'll come back to this in a minute. If my system were quasi-linear, remember what would happen? The pain in the neck term would go. When I multiplied through and averaged, I wouldn't get this term, and so I would never need the third cumulant. And so I would never need to solve for it. And so what I could do is I could truncate my cumulant expansion at second order. Okay, I just have a second order cumulant expansion, and we call this thing CE2. So for a cumulant expansion truncated at second order, that's going to be CE2. I could, okay, so the Lorentz system is not going to be very well described by a quasi-linear. The Lorentz system is about as non-linear dynamical system as you can get. It's not going to be very well described by a quasi-linear type system. So we might want to go a bit further. And so we might want to go a bit further and do CE3, which is a cumulant expansion truncated at third order with some model for the higher order cumulants. Okay, and I'll come back to modeling in a minute. So what can we do? We can solve for the PDF. I mean, we can solve it just numerically, work out a PDF, and we can then solve the cumulant equations and see how well that they reproduce the mean and the covariances of the system. Now, I want to stress again, the Lorentz system, I think, is harder thing to do than anything you'll ever do in fluids. And one of the reasons is because there isn't really very much mean. In fact, there is no mean in some of the variables. X doesn't have a mean. Y doesn't have a mean. It's only Z that has a mean, okay? If you have a look at a time series for X and Y, they kind of bounce around 0. It's only Z that has a mean. So this is a pretty severe test, I would say, for a cumulant expansion. And it doesn't do too badly if you go to third CE3. Depending, and we get slightly different results depending on what you choose for this. It's called an eddy damping time. I'll come back to that a bit later on. Okay, so I don't know, let's do a non-trivial one, which isn't 0. Let's do this one. So this is let's do this one. This is even harder to get. This is 2-point correlation function or covariance matrix between X prime and Y prime averaged. And you can see DNS is about 4, and these guys are not too bad in terms of predicting this. Okay, So that's all for ordinary differential equations, okay, just to give you a feel. What about for partial differential equations? Well, one way you might want to do it is just to turn your partial differential equations into ordinary differential equations. You all do that to solve these things numerically. So you might do a spectral expansion if you were solving these things spectrally, and then just write down the equations for your spectral modes. That's one way of doing it. The other way of doing it is to just go through the algebra in real space, as it were, and write down equations that you would like to solve, and then solve those spectrally. So whatever your favorite numerical scheme is for solving your usual PDEs, you can still use for doing your Cumulant expansions. And in fact, one of the papers, I probably won't have time to show you, but one of the papers which has done this uses Daedalus, the Daedalus thing, to solve the Cumulant equations for the Bussard annulus, which is the one I showed you before, where we were doing QL and GQL. So, okay. So how do you do this? So remember, I had my set of PDEs. Okay, so it could have all of these things. Okay, I've written it out here. I define my cumulants. So I do my Reynolds decomposition. Sorry, I've used angled brackets here as opposed to bars, but that doesn't really matter. So C1 is the first cumulant, it's the mean. Second cumulant now is a covariance, so it's a 2-point correlation function. The third cumulant is a 3-point correlation function. And then I either use some kind of hot functional technique, which again, I'm not going to go into, but it is in the notes, or brute force. And we derive schematically a set of PDEs for the cumulants that look like this. So I don't want to labor the point, but C1 dot is linear in C1, but I need C2. C2 dot is linear in C2, but I need C3, etc., etc. So as I put here, if I truncate at second order, meaning I set C3 to be equal to 0, this is a quasi-linear, realizable, we all know what quasi-linear means, self-consistent mean field theory, which we call at CE2. And for those of you who know about this work, statistical state dynamics, it's called, it used to be called stochastic structural stability theory. This is formally, if I stop here, this is formally analogous to the work of Farrell and Ioannou, who derived these things a completely different way, or came to these things a completely different way. But you don't have to stop at C2. You could put C3 in. So truncation at third order, if there are any turbulence experts in the audience, this is an anisotropic, inhomogeneous, what's called eddy-damped quasi-normal Markovian approximation. Okay, that's a tough thing to say. Yeah. Yes. So this is an anisotropic. Yeah, that's right. I don't know. That's an interesting question, and if there's something you would want to impose like that, I don't know. I'd have to think about that. Okay, so this is just a slide on the Hopf equation. I'm not going to go into details. So just to remind you, if I truncate at second order, okay, what am I including? I'm including a mean interacting with a fluctuation to give me a fluctuation. I'm including a fluctuation with a fluctuation to give me back the mean, but I'm not including the fluctuations, okay? Now then, this looks like a very funny way. Sorry, I should explain what I'm writing here. The evolution, I've probably still got the order. Yeah, okay. Let's do this. So this is the evolution of the mean thing. So think of this as Q bar, right? So the evolution of Q bar, so that term is this term. There's a linear term here acting on the mean. There's a term of the mean acting with the other mean. So that's this one. And then I've got this funny term here, which is like the nonlinear, it's this term, but written in terms of 2-point correlation functions. And what you're doing by doing this integration with the delta function is taking the 2-point correlation function and bringing those points together. And then that turns into this term. It looks like a funny way of doing it, but once you're expanding things in 2-point correlation functions, you want to find this thing acting at R1, you have to integrate with the delta function. And then the evolution equation for the second cumulant looks it just has linear terms because I got rid of the pain in the neck term if I'm at second order. Okay, so it just has this term and this term. Okay. So I'm going to show you how well that works for a problem. And the paradigm problem I'm going to look at is this so-called barotropic turbulence on a sphere. It's 2-dimensional hydrodynamics on a sphere. And this is one of the ones I wrote down earlier in the first lecture. And it's an evolution equation for the radial component of the vorticity. There were various linear frictional terms that I put down here. This is a hyperdiffusion just to get rid of the small scales. This is the nonlinear term. And this is the stochastic driving. Okay, and we're going to solve this using spectral techniques on a sphere. There are lots of other problems which have been looked at for CE2. And I'm going to compare two techniques, one of which is using just DNS. I'm going to call DNS the truth. I'm one of those people who doesn't really believe DNS is the truth, but let's call it the truth for the minute. And then I'm going to compare it with a fully spectral direct statistical simulation where instead of solving for the large and small scales together, we're just going to solve for the mean and the 2-point correlation function. Okay, so before I show you how well these things compare, I want to tell you what we might expect from this. I know you're not really geophysical fluid dynamicists necessarily. What do we expect? Well, we expect the small scale turbulence will drive jets via what's called PV, potential vorticity homogenization. And I'm not going to go into the theory for that, but I've already shown you a movie of this happening, but I'll show you the movie again. So, okay, so this is the movie we saw before. I force at moderate scales. The flow goes turbulent. Here's the flow going turbulent. There's a different projection of it going turbulent. I'm looking at zeta, the radial component of the vorticity. And after a while that we're ticking around, this is keeping track of the number of rotation periods. The system sorts itself out such that it's all red, or quite a lot of red. This is positive radial vorticity in the northern, and all blue in the southern hemisphere. And this is a sign or signature of an equatorial jet. So hopefully you remember that movie. So the question then is, what are the means and the 2-point correlation functions? And how well does DSS, the direct statistical simulation, do at capturing those? So what you can do is you can do an average, you can do a longitudinal average to try and find out the mean. So let's have a look at this one. This is the radial component of the vorticity. This is the actual zonal flow. So at each point in time, the zonal flow is kind of bouncing around. So it's a kind of, even if I've averaged in phi, it's still a function of time. But you can see there's a fairly well-established zonal flow with an equatorial jet. Actually, at the towards the poles, there's a backflow, a so-called retrograde jet. And then at this point in time, in order to do a comparison, we're going to start doing a running average in time. So by the time we get here, the statistics have settled down. And that's what we're going to call our mean. And we're going to have a look at how well CE2 does at reproducing this. Now then, I'm just going to show you a movie, but if you go and talk very nicely to Brad will give you a demonstration of him solving the CE2 equations for this problem on the laptop. You have to talk very nicely to him. I should say the DNS we did took quite a long time to do. You know, so it's quite well, it's not a massive 3D calculation, it's only a 2D calculation. It still took a long time to do. Now I'm going to solve the 2-point equations, and you very quickly go to a fixed point. Sorry, I'll explain what all these things are in a minute. Is that the movie done? Oh, that was quick. Oh yeah, it is. Okay, remember, that's a very short movie, so let me try and stop it at the... Oh, no, keep going. Okay, the mean is coming. Here's the mean. This is almost as fast as it takes as it does to solve it. Would that be a fair thing to say, Brad? Yeah, this is almost. So we're stepping towards a fixed point in space. We're going to get the means here. And what you're going to see in a minute that's a mean. Okay, and this is the covariance function. So this is the 2-point correlation function. So what we're plotting here is the cross correlation of all the other points that you can see with this point here of the vorticity. Okay, and so we can show this very easily because we're solving for it. That's what we're solving for. Okay. Okay, so let's do a. So what do we see if we do the same thing? Well, certainly direct statistical simulation at CE2 does reproduce the driving of at least these jets. Okay, now there was a theory that these jets were solely driven by an inverse cascade to larger scales, which led to the formation of these jets. But that can't be right because CE2 is a quasi-linear theory. And I told you in the second lecture that quasi-linear theories throw out cascades and inverse cascades. So this is the direct driving jets by Reynolds stresses. So these jets are therefore driven directly by Reynolds stresses. As I say, recall there is no inverse or forward cascade in the model. So let's just do a comparison. So DNS is here. So this is the equator, the jet, the equator, and you can see the 2 retrograde jets. And CE2, with different resolutions, does very well at getting the amplitude of the jet at the equator. It doesn't do so well near the poles, and we understand why this is. And if I have time, I'll explain why this is, or you could ask the question. Okay, it says it here. Okay, it's because of where we force the turbulence. There's no turbulence force near the poles, so C2 is a theory which can't scatter energy. Remember, I talked about there's no eddy-eddy scattering. So in order to get energy at the poles, we can't do it under the auspices of CE2. Okay? But it does quite well. And how well does it do getting the 2-point correlation functions? Well, not too bad. So if you look at how well you can calculate this from DNS, you look at the correlation function here, and you see, I don't know, it's quite, there's this wave-like form. This is a signature of Rossby waves. It's quite localized, meaning you only really have power kind of up to here. And when you look at C2, it captures the 2-point correlation function reasonably well, but it tends to overstate the long-range correlations. And that's a drawback of the of CE2. Okay, I don't have time to talk about that. So in the last 10, 15, yeah, sorry. Yeah. Yeah. Now I'm doing a cumulant expansion under the quasi-linear approximation. So let me go back and I'll show you. So yeah, let me just go back in. So it's here. I mean, this is what we solved. We actually solved these equations. And the quasi-linear approximation has come in by the fact that we don't have anything else here. because we've dropped this term, and that has led to the third cumulant not appearing in the equations. So this is a closed system of equations, so we can solve them. These are PDEs. We're solving these PDEs. No, so this really is not, we're not solving for the whole PDF, we're just solving for the low order moments, low order cumulant, sorry. Yeah. Okay, sorry. So I have about 10 minutes left, so let me just do a kind of smorgasbord of results. So how could you improve on this? This is pretty good, but how could you improve on it? Well, we could try and generalize the quasi-linear approximation, which would be a good thing to do, and we have done it. We did the generalized quasi-linear approximation. And as I said at the end, the reason we wanted it to remain linear in the high modes was that we could then try and derive a statistical theory corresponding to GQL. And we've just done that. And Brad and I are meant to be reading the paper at the moment. Brad had COVID, I'm lazy, so we haven't done that. But my postdoc, our postdoc Girish, has put a lot of work into this. And he's just managed to get GCE2, what we call GC2, a generalized C2 to work. So we'll put that in probably in the next couple of years. We'll get around to reading that and get it done. Or you could not stop at C2, put in the third cumulant or some model of the third cumulant. And we did this a few years ago. Yeah, okay, the best place to look is on the archive. This is in a book which nobody can get hold of and came out 4 years later. So if you want to know how C2.5 or C3 does on the problems that I've shown, then you can have a look. You could also change the definition of averaging to ensemble averaging. And I'm not going into details. But just very quickly, let me just talk about this one. This is one where we put in C3. If we put in C3, we start to be able to scatter energy towards the poles here. And we get a better approximation to the zonal jets. But as I say, if you want to see that, you can have a look at the paper. And here's a summary of how well all these things do. And you can see we've got something there for GC2 as well. So down here, these are the kinds of things you solve in real space. So nonlinear, QL, GQL, and these are the statistical flavors that we've looked at. Okay, yeah.
That's the specific instances of the nonlinear GQL, right? Not like an ensemble linear, something that's closer to where you're showing effectively in the right-hand side.
Sorry, say that. GQL would be an effect, yeah.
Each of those is like one instance
Yeah.
or something, whereas the right-hand side is like
Yeah, okay, and that's right. And so the slide I skipped over about what's the difference between doing an instant, one example of say QL versus a statistical theory like C2, you would expect the two to agree, but they don't. And we've just written a paper which was just literally on day, maybe Tuesday, rejected for being too mathematical. About why these two things don't agree, yeah, or why they might not agree. Yeah.
Is there like, maybe this is asking too much. Can you say how fast, how long?
Yeah, you're right. It's asking too much.
Okay.
Yeah. I'll talk to you afterwards. I mean, Brad, did you want to comment on that? Yeah, there you go. Okay, so I'm going to finish very, very quickly just by saying, how might you try and make CE2 or CE3 or any of these things faster? Now, I didn't dwell on this, but remember I talked about trading nonlinearity for dimensionality. When you're solving for CE2, what you're solving for is a 2-point correlation function. So if I start off with, say, a two-dimensional partial differential equation, my 2-point correlation function is 4-dimensional. Now I can use symmetries to get that to 3 dimensions if that's available, but in general, it's not available. So what you might want to do is cheat or truncate, as we like to call it. So I could write my second cumulant, which looks like this, as a sum. I could just do what's called a POD, or principal component analysis, via a Schmidt decomposition. And maybe I can still get quite a good answer just by keeping the first few modes, okay? So if I take something, I don't know, this is a typical cross-correlation function, a covariance matrix correlation function, which looks like. And if I keep all 600 modes, it looks like this. If I do a POD decomposition, most of the structure is contained in possibly like the first few modes. So it might be that I only need to keep these and I can forget all about these. So instead of solving for a very large dimensional second cumulant, I just keep the first few modes. Okay. In fact, this is the structure of this thing if I just keep the first 3 modes. You might say, well, that's not bad, actually. The problem is, you don't know which modes to keep until you've done the calculation. Right? You're expanding in the basis of the answer to the solution. So we showed that this works quite well, assuming we knew the answer. So we did the full thing, we worked out this spectrum here, and we said, let's just keep these modes. How well does it do? It does brilliantly, and it's incredibly fast, incredibly fast. Ideally, what you'd like to do is try and work out which modes you need as you're going along. So, okay, very quickly, this is work my postdoc Quan has been doing, and we're still trying to understand what he's doing. So the question we were asking is, can direct statistical simulation be used dynamically? So this is trying to combine DNS with BSS. So if you're doing this, what you're thinking of doing is taking something on a very fine grid, doing DNS on a coarse grid, and then letting DSS take up the slack, as it were, and try and do the rest. So I'm going to think of the first cumulant as the DNS solution on the coarse grid, and the second cumulant then is the correlation of fluctuations of all the resolved scales projected onto the coarse grid. Yeah. So this is very expensive. This would be very expensive if you kept the full second cumulant. So what Quan has done is he's just kept the first POD mode of the second cumulant. He can keep the first 2 or the first 3, but he just keeps the first POD mode. And he has a very clever way of doing it, which I don't really understand. Okay, so again, we have, well, I'm not going to go into details. We have this set of equations, okay. He's going to define the first cumulant as the solution on a coarse grid. He's going to define a second cumulant in terms of its Schmidt decomposition. He's then going to evolve the first cumulant. So if I put H equals to 0, this would just be under-resolved DNS, if you like. Then he's got this term H. H comes from solving for the second cumulant, and you just keep one of these eigenvectors or POD vectors of the second cumulant and bung it in. And you can try doing this for C2 or for higher order expansions. And he's tried this on a model. He's tried this on various models. What I'm just going to show you a movie of is this so-called Hasegawa-Wakatani equation, which is a model for driving of zonal flows in tokamaks. And for those of you who are still awake, were paying attention, this has a very similar structure to the Bussa annulus. So if you don't like Hasegawa-Wakatani, we could probably do this for the Bussa annulus. Let me show you what that thing does. Why is this not working? Oh, it's down there. Okay, so this is DNS of the different fields, and it's very similar. This is the vorticity. This is number density. You think of this as temperature if you were doing the Busse annulus. And we get these zonal flows. I mean, that is a model of the generation of zonal flows. Okay. We have structure on many, many scales, but we're going to be interested in zonal flows. That seems to be the same. Okay. Okay, twice. So then what we try to do is do some comparisons of DNS at 120 squared, DSS at 30 squared, plus 1 mode for the second cumulant. Again, we still don't understand quite why it's so good. So I don't know, keep your eye on your favorite one. Yeah, this one's a good one. Washes all. But I mean, the thing to take is, I don't know why this is flashing around. If you do a comparison of DNS with DSS, it's not doing badly. The reason these are shifted is because there's a it's periodic, so there's symmetry. So we could shift it anywhere we liked and line these things up, but we didn't. So we're still working on this. I won't say we're on top of these things. I don't know why all these slides come in twice. So just to finish, almost bang on time. So after 3 lectures, what have we learned? Well, methods from non-equilibrium statistical mechanics could be useful in determining the statistics of geophysical and astrophysical systems that include the interactions of mean flows with turbulence. And we call this kind of direct statistical simulation. You can move beyond quasi-linearity either by going to higher order in the cumulant expansion. So that includes some, if you like, models of triple correlations. Or you could try generalizing to the quasi-linear approximation. So I spent a lot of time looking at GQL, and now it seems like we can have a statistical theory for GQL. You can speed up significantly, perhaps by using a reduced basis. You have to try and think about what reduced basis you want to need. The technique may, if we're lucky, form a basis for conservative statistical subgrid scale models. And even if you're not interested in subgrid models, but you're interested in just simulating larger scales, which we might be for astrophysics, this may offer a fast, efficient, conservative, self-consistent mean field theory. Okay, so thanks for your attention, and I'll leave it there and take questions. Who are you pointing at? I can see you, but you're pointing at somebody else.
I've got a question about the sector. Like zonal flow. Had the mean of CR1 by CR1, not CR2, right? You don't have you have the equal point.
Yes, yes. Okay, because, imagine, I mean, that's right, you could write down evolution equations for everything at a single point. So you could do that. The problem with that is it's very tough to do things like maintain energy conservation, things like this, unless you put it in by hand. And so, you can always put these things in by hand. We wanted something that worked for all situations. And if you believe that, things that occur today at here at this location depended on things that occurred, I don't know, yesterday, 3,000 miles away, you have to get these. So these cross-correlation maps that I showed you in the atmospheric community, I think they call teleconnections or something. And for some, they think they're very important. If something happens in the Rockies, 5 days later, we're in trouble in the UK. So it's that kind of thing, this non-locality in space, that's important to get. You may have noticed we haven't done anything about non-locality in time. So if there's a significant memory affecting your turbulence, this won't be captured by this. These are equal time statistics. You could put that in by putting in memory kernels or something like that, but that's not captured within the framework of this. Yeah, Alan.
Kind of alluded to this in the earlier slide, but if you're interested in rare events, like comparing to players or videos,
Yeah.
what do you think is the best way?
Okay, the only thing I would say is Freddie Boucher has some great ways of trying to work out rare events and trying to have techniques for simulating. Let's say you have your Geodynamo code or something and you want to watch it reverse. Well, in general, you're spending most of your time just hopping around it, not reversing. So there are techniques for trying to get this thing to go to the bit of your simulation where it will be likely to reverse. And Nigel, I'm sure, knows a lot more about this than me, but it depends on kind of instanton theory and things like this. So I would say watch Freddie's lectures at this school. I mean, he gave 3 lectures, I think, on this thing. So. Okay, you better, oh, go on. I was gonna say, you better have left me some tea, but go on. Sorry, I didn't hear you. Are these things a solution of the Navier-Stokes? Oh, POD modes. Well, if you keep all the POD modes, let's say you do a simulation of the Navier-Stokes equations, and then you decompose into POD modes, and then you keep them all, and you evolve them all, then you would get it's just a different basis to do your calculation. So we're doing it in the POD modes, though, of the second cumulant. We're expanding the second cumulant in its POD modes. Yeah. Yeah. Okay, so for both of those cases, the conservation laws are respected because remember I said I was taking out triad interactions in pairs. So it's like if I'm a mode and I give energy to that mode, and I take out that interaction, and I also take out the fact that this mode can take energy from this mode, then I'm okay. It just has to give it to some other modes. So the global conservation laws are respected. If I go to C3, then that's not true. Yeah. Yeah. How do I get the POD modes? Okay, so I literally do it by brute force. I take the so the first one we did. Sorry, go back. So the one we did was we did the DNS. Yeah. We worked out the second cumulant, and then we just worked out its eigenmode. So that's the one I described as cheating. Yeah, because I had to know the answer to get the answer. Yeah.
Provide some comments on how is the closure with statistical method compared to the PDF backfill of separate closure by Professor Pope.
Oh, I'd have to think about that. It's a good question. Yeah, let me think about that. I'll get back. Yeah, I'm not quite certain which closure you're talking about, but maybe if we talk about it, we can. Yeah. Okay, thank you all for listening. Let's go and get some tea.